Hello, everyone. Welcome to today's webinar titled Incident Response and Forensics in a Cloud-Native World with Neil Carpenter, Principal Solution Architect here at Twistlock. I'm excited to get started today and introduce Neil. We're just going to wait a few seconds as the last few folks join. I just want to mention a few housekeeping items before we get started. You're welcome to download attachments and links that we've included here in the BrightTalk console. We have a summary about our incident response and forensics capability that Neil put together, as well as one of our latest white papers and data sheets if you're interested in learning more about the Twistlock platform. And let's kick things off. You're also welcome to ask questions throughout the webinar that we've saved some time for at the end to answer. And as a reminder, this presentation will be recorded and you'll all receive a copy soon after it's complete. I'm proud to introduce Neil Carpenter. Neil spent 20 years at Microsoft, including 13 years investigating computer security incidents on behalf of customers. He also developed and maintained tools used for gathering and analyzing incident data from Windows hosts, developed methodologies for emerging trends and compromises, worked closely with Azure and Office 365 security engineering organizations, and spent as much time as possible passing on knowledge to emerging engineers, Microsoft's field organization, and customers. In his spare time, Neil is an active street photographer. Welcome, Neil. Thanks for leading today's presentation.
Thanks, Keith. I think I'm going to get you to come along to introduce me all the time. So let's jump in here and talk about what we're going to talk about. So I want to start with a story here. Keith mentioned that I did a lot of work with Azure and Office 365 at Microsoft. And they were both really interesting platforms for a reason. For me as an incident responder, they were interesting because they changed assumptions and they changed approaches to incident response for customers that had gone those directions. And the other thing about them was they invariably happened for reasons that the security team in the company had nothing to do with. So they would suddenly find that things were deployed in Azure. They would have a security incident in Azure, and they would have no idea how to respond to it. And I spent a lot of time building out approaches and methodologies for both of those platforms. One of the things that interested me in containers in Docker and cloud-native environments was that they're very much going through the same cycle right now, where people are deploying containers either for very, very high-level business reasons or because DevOps and developers are very excited about the capabilities that they bring to the table. And these things are washing past a lot of security teams who either have not been able to get their arms around it or, on the other hand, are putting barriers in place, slowing down the implementation of agile approaches to development. So it's a very interesting space for me today. And so what I really want to do is I want to start out with taking these two I don't know, a lot of people think developers and security people are natural enemies. I'm not sure that's true. I think there's a lot of misunderstanding. So what I want to do is start with talking about incident response for DevOps folks, give you an idea of what goes into it and what we're thinking about. And then come at it from the other direction, talk about what containers mean for incident responders and for security orgs all up. And then put that all together into a cohesive set of thinking about how you approach finding and responding to security incidents in a containerized environment. And then finally, we're going to look at some of the things in Twistlock that we're doing specifically to enable customers in this area. So with that out of the way, let's start with, first of all, incident response and for DevOps. So when I think about incident response, first of all, you'll frequently hear the word forensics used. And we're going to use forensics occasionally in here. But generally when I'm talking to people, I try not to use that word because it technically means developing evidence for use in a court of law, which is really not what we're interested in when we're talking about incident response in most corporate and government settings. Well, government's a little different, but in most of the settings we're talking about, what we're interested in is not putting handcuffs on wrists. What we're interested in is maintaining business continuity and protecting our data. We're interested in finding attackers who are either successful or may be successful, limiting their ability to do what they're going to do, and then taking that off the table and figuring out what happened. Were they able to access data that's important? Were they able to establish persistence so that they can come back in time and time again? And this was the sort of work I was doing over and over again, is going into a customer who's found a potential security incident, investigating, figuring out what happened, and then figuring out what the impact is. And so the approaches to that, so a lot of the approaches, going back to the word forensics, a lot of the approaches come from early computer forensics, which were very much focused on putting handcuffs on wrists. They were focused on developing data that you could use to identify a perpetrator, stand up in court, talk through what happened, and make a conviction. Now, those approaches are heavily focused on gathering data from hosts. Disk imaging, memory imaging were main keystones of a lot of forensics approaches and a lot of incident response approaches. And even if you're not doing disk imaging, for instance, which is not something my team used heavily, you are relying on that host being there to gather data from it and work through that data, log data, event logs, files on disk, etc., and then using that for analysis. And in fact, in a bigger picture, NIST, the National Institute of Standards and Technology, has a great guide to developing an incident response program. And I borrow this image in particular from them because it's the whole life cycle of what we have to do for incident response and how we're going to approach it. Starting with preparing for it, which we're going to talk about heavily. So in containers, I think preparation is more so the key than it is in traditional environments. The next piece is detection and analysis. And so I've got to be able to find when there's anomalous behavior. And then when something is a potential security incident, and when I say incident, that means anything that violates your security policy. So that may be something unintentional, that may be an attacker, that may be an insider doing something outside of acceptable behavior. But once I find those things, I have to contain that, I have to eradicate that, and I have to recover from that. And then I have to take all of my learnings and fold those back into my preparation and do better next time. Now, one other language thing I will caution folks on. I tend to refer to security incidents. You'll see the word breach used a lot. Don't use the word breach unless you really know what it is. Unless you really know what it is in the situation you're talking about. Breach is generally used to refer to the actual loss of sensitive data. And so as soon as you use the word breach, people get much, much, much more concerned about what's going on. For me, as somebody working with other customers and other companies and other people, I keep it to security incident, and I let them determine if there was a breach or not. But so this is really a brief overview of what incident responders do and what this looks like. Now let's go to the other side of this. So from an incident response perspective, the incident responders I know are really, really familiar with sort of traditional desktops, servers, disk arrays, all of these things. Containers, everybody I've talked to in the field don't really even have their arms around them yet. So what I hear most frequently is, they're many virtual machines. And that's not really the case. So what a container actually is it's a user mode only. I suppose saying a container is redundant. But it's taking just the user mode piece of a running application and sectioning it off into its own namespace so it runs isolated from the underlying host. So there's some really key benefits to this that enable what we call cloud-native approaches, cloud-native development. And one of the first ones is infrastructure independence. So one of the things that's magical for me is once I put things in containers, I can configure them exactly how I want them to run, and I don't have all of this sorts of underlying dependencies and configurations and everything necessary. So what this necessary to run whatever the application is. So what this allows me to do is I can take a thing and develop it on my desktop. I can run it on my desktop with all of these containerized components. So I can have, my application logic and my front end and my database and all these other things running in containers on my desktop. I can then shift that to a bigger development environment, my pipeline where I'm building things for production. I can then shift that to a test environment. I can then shift that to production on-prem, in the cloud, in multiple places, in multiple geographies. And in every one of those places, it's running identically, and I didn't really have to do any significant configuration on my desktop or on my cloud service provider or wherever else. So that's really magic, and that enables a lot of agility and development where I can build this thing out, see how it runs, and push it out and have it run predictably wherever I run it. This also leads us to what's called microservices, which is the other major component of this. And that's the idea that to enable me to do that, I'm breaking my application out of this sort of monolithic thing into microservices, little tiny pieces of it. So I'm taking each sort of functional piece of my application. So the front end of my website, I'm breaking off from the rest of it. It's one container or one image that spins up one or more containers. And then I'm taking some logic and putting it in a separate service, and I'm taking my data and breaking it up into very small pieces. So where I might have had, a typical three-tiered application where I had some data components, some application logic, and a front end, I might now have, if you look at some of say the sample microservices applications, like Weaveworks has they call it the sock shop, which is a sample microservices app I use a lot. It breaks that three-tiered application out into about 15 different services. So now I get these little pieces that each represent some functional piece of what I'm doing. Now that also, from a management perspective or from a cost perspective, enables computational density. So now, since I have these very small pieces, I can stack those up and more efficiently use my hardware, especially since it's broken out from all the other layers. They're independent. They can run independently. I've now got the ability to take and pack these things in very densely on the servers that I'm running, whether those are on-prem or in my cloud where I'm paying by the CPU cycle and by the machine, et cetera. I've got the ability to quickly enable that. Now, this leads to another thing though, which is that these are, by definition, my containers are ephemeral. They can spin up and go away at any time. Any data that I have, anything that has to be persistent, is supposed to be stored somewhere else. It's supposed to be stored in a file volume. It's supposed to be stored in a database, in some sort of object store somewhere else. So I have to take into account ephemerality, ephemeralness, that all of those individual containers, unlike, say, my laptop, my server, my VM, which have predictable life cycles that are managed by me, right? My laptop sits on my desk until I'm done with it, and then I flatten it and recycle it or whatever. My server sits in a rack. My VM is controlled by my cloud service, but I have visibility into when it spins up and when it spins down and where that is. My containers are all managed by somebody else, and they're spun up and spun down as needed, and they can go away at any time, which is a real challenge from an incident response perspective. And obviously, that was a very, very brief introduction. I would encourage you, if you're in an incident response role, this is of interest. If you haven't already, spend some time with containers, walk through some of the Docker samples, and start experimenting with this stuff. But let's take these things and put them together and talk about sort of what it means. So first of all, if I take my traditional approaches, gathering, say, what's in the file system, well, this becomes challenging because my containers spin up and spin down, but also because what's in the file system is sectioned off. Now I can image the underlying host and get that file system data, but now I have to spend a lot of time picking through it to figure out what applies to the container I'm in versus what is in the rest of the file system. Now there are some approaches. So Docker export is a command that will take a running container and export a disk image as a tar.gz. That's an approach to gathering that data. You still will have to account for if you've mounted volumes from other places. So if you've mounted something in NFS or in one of your cloud services providers or somewhere else, you have to account for gathering that data as well. So it's not undoable, but it's problematic. Gathering memory images is much more problematic. You can gather an image of the underlying host's memory. Once again, you're stuck with figuring out how am I going to pick through that, find the memory that's relative to the container I'm interested in. I haven't found a good approach to this yet. I don't want to say it's a dead end, but I don't think there are strong approaches to it yet. I may be wrong. Somebody may have solved this problem, and I just haven't seen it yet. I don't think there's a great approach. But all of these things are problematic because you can't count on that container being there. If you're running Kubernetes or whatever you're using to manage your containers, generally they're going to spin up and spin down as necessary. And so you may find an incident now that happened 5 minutes ago or 5 weeks ago. You have no guarantee that container that was in still exists, or that any of the artifacts associated with it still exist. So this really necessitates a different approach to these sorts of incidents. And I think it's really focused around logs, telemetry, and flight data. And this is where you really have to think about planning ahead as you're moving into a containerized deployment. So first of all, application logs for what's actually happening inside the applications you're deploying. Now, traditionally, you may be sending some of these logs to your SIEM, to Splunk or ArcSight or whatever else, but a lot of times in my experience, that wasn't happening. The expectation from an incident response standpoint was if my web server got compromised, I could go to my web server and pull logs from there at that point. So you have to have a real plan to capture those logs coming from the application, and also to make sure that what the application is logging is sufficient to reconstruct an incident inside of the application. So making sure that logging covers everything that your responder might need, to the extent that you can gather that data, to the extent that you have storage to gather that data, et cetera. But it's very important to plan ahead if something goes wrong in your web front end. What's in those logs? What data is available there, and is that sufficient? And if not, what can you do to augment that data? Now also, you have container logs. So Docker itself, or the underlying container engine itself, is logging everything, essentially everything going to standard out from the container. So this is another source of data that it's worth capturing and maintaining to reconstruct not just what was happening inside the application, but inside that wrapper, that container that it was running in, everything that's there. And there are approaches, there are plugins for Docker, for example, to log to various sources or destinations, I guess. There are approaches to this. There are lots of ways to do it. Some of the cloud services as well have very specific approaches to doing this, but it's important to make sure that we're gathering that data, we understand what's there, we understand how to approach it. And then finally, I think the emerging, and also obviously logs from the underlying host. So syslog, that sort of data is going to be important as well, especially if there's a potential risk of a breakout of the container and a compromise of the host, which there are configurations of containers that by design allow for that. So making sure we have syslog and whatever other data we want to gather from the underlying host. Now, in most shops I've worked with, that is data that's already being gathered, but it's important to account for it here. And then finally, the other thing that I think is an emerging approach here, and certainly in other markets as well, containers are not the only place you're seeing this happen, but it's really, really critical in a container market or in a container deployment, is an idea of a flight data recorder, something that is capturing state data, that's capturing ongoing transactions, other things that are happening that you otherwise wouldn't have visibility into, and recording that at a level that makes sense, once again, for your storage requirements and for your investigation requirements and for your monitoring requirements. Gathering that data and having it available when something happens to review and reconstruct an incident is very, very critical. And I think that this is where a lot of work's going in, certainly from Twistlock, but from other companies as well that I've seen. So with that said, I want to take a few minutes to walk through where Twistlock is on this and then show you what this looks like in practice with a couple of incidents in my lab. So starting off, Twistlock has strong runtime protection, monitoring and protections. And we're pushing towards a learning approach. Instead of just building out rules and having some smart security people who have to write rules and keep up with the pace of change, we've approached this as let's learn as things are deployed what happens inside of them. Now, there's a couple of reasons for this. as we move into a DevOps cloud-native world, the pace of change is ramping up. That's one of the reasons we're interested in using containers. I talked about this earlier, right? It's agile. It lets us move really quickly, deliver things quickly. Because they're microservices, we can change one component and not have to worry as much about the other components involved. So instead of shipping maybe 3 to 4 times a year, now I talk to customers who are shipping things every day. So there's new code going every day. Not only that, in the DevOps world, most companies tend to have now more developers feeding into the same pool of smart security people. That's not to say there aren't smart developers. I'm a security person. That's sort of my bias. But it's really hard to grow security teams right now. And so we're pushing more developers, more code, more frequently through the same number of security people. It becomes harder and harder to keep up with writing rules and making sure that they represent new code that's shipping more frequently. So from a Twistlock perspective, we're trying to take a lot of that drudge work out and allow the security folks to focus on the edge cases and the anomalous behavior. And how we're doing that is we're learning as I push new images through my pipeline and into execution, what do they actually do? What processes should start up in that container? What network activity should there be? What file system activity should there be? And, in the past on desktops and servers, we've looked at approaches to doing this sort of learning, not we Twistlock, but more generally the industry has looked at it. And it's been difficult. If you try to do this on my desktop, I'm doing a million things there. I'm running a million different things. Whitelisting approaches on desktops and even on servers are very difficult because they are so broad. They're doing so much. In containers, by virtue of being microservices, by virtue of being tailored down to do just a handful of things inside each container, this is not trivial, but it's much easier to do, and it's very, very powerful. Also, syscalls are mentioned here. Through our research, we found that what was more appropriate for syscalls was instead of learning, we take a model of whitelisting appropriate system calls, blacklisting potentially dangerous syscalls. And so this is fully automated. As things are deployed, this just happens. Now I can also control it via API if I want to have sort of a more mature, more automated and repeatable pipeline. But if I deploy Twistlock today and start pushing things into my container host, this is going to happen automatically. So, and then this combines a number of things. Ultimately, all of these things combine into the ability to generate audits, generate alerts when there's anomalous behavior. And one of the nice things about this is this means that instead of getting everything that's happening across all the predictable and repeatable behavior, we're highlighting only those things that are anomalous, only those things that violate the models we've generated plus any rules that you generate. So once again, this is about extending that security team we have, using them efficiently. Instead of generating, an excess of data, we're generating data that represents variations from expected. And then I can also use that as a template for preventing these things. So preventing, for example, a process that starts up that's not in the model we've built out, or even doing what we call blocking. Blocking takes a container completely offline, and thus I think of it as being great for high assurance environments. If I have containers that are dealing with sensitive data, credit cards, financials, customer, sensitive things. If I have containers that are dealing with that, I may want to take a more draconian approach when an anomaly happens. Take that container offline so that at least the file system for that container is maintained. I can do traditional forensics on it, in addition to all the other things that we're enabling. In the meantime, my orchestrator is going to fire up another copy of that container, so my business is going to continue to be handled. I'm going to be able to handle the load. But the container where the anomaly happened is waiting for my incident response team to pull it apart and figure out what happened there. Now, we've also added a forensics incident response targeted capability. And this goes back to that concept of a flight data recorder. So we have a flight data recorder running on every node that we're protecting with Twistlock, every virtual machine, every Docker host. That's gathering a circular log of data about all of the containers running there. So what's happening inside of those containers? And then when we detect a potential incident, when we detect a combination of factors that make Twistlock think there might be a security incident there, we pull out the relevant data and save it so that our incident response team can get that flight data to correlate with the container logs and the application logs and the alerts that Twistlock has generated and all of the rest of this. And that's really what I want to show you here in a moment. So, this is really a key component, not just stopping the kill chain. In an assumed breach world, we can't always stop the kill chain. We're going to do our best, all of us, Twistlock, your deployments, etc. But the reality is that in this world, sometimes an attacker is going to be faster, smarter, or luckier than we are on a particular day. So it's not just about stopping it. It's about being able to respond and investigate and figure out what happened on the day when that happens. So with that said, let me switch over here to my console and show you a few. These are obviously not real incidents. These are incidents I've created in my lab, but give you an idea of what, from a Twistlock perspective, an investigation looks like. So the first incident I want to show you, this is a PHP server that's running in my lab that somebody was able to create. I'm the attacker. I'm the black guy here, the black hat here. I was able to create a reverse shell and then run some things in here that were unexpected. So I can see here we've generated an incident. Here are all the details of this incident. From here, I can really quickly assess what's my risk from this reverse shell. And I can see down here, we have some process audits, something ran that wasn't in the model. We have some network audits indicating that there was unexpected outbound traffic outside the profile for this container. So with that in mind, that gives me an idea of why we're highlighting this. From here, I can go see, all right, where's this running? What configuration risks, what compliance benchmarks is this particular container running afoul of? And I can see here I have a Twistlock specific benchmark. There are secrets in clear text environment variables. And if I dig in here, I'm going to see that the MySQL password for this container is available in clear text. So an attacker who compromised this was able to get that password from here. I can also dig in what vulnerabilities exist here. This may give me some solid data on how was an attacker able to compromise this container and get into it. I can also see it's running currently in 3 containers. I can go dig in there. And then I can also see where does this container fit into my bigger environment. From the radar view here, I can see here's PHP server. That's the container that actually has this issue. I can see it has connectivity to a MySQL container. I sort of expected that, knowing that the MySQL password is present here. But now I know not only did an attacker potentially have the password, they have connectivity to that MySQL database. So based on, I would have to go dig in and figure out what sort of access does that account have to the underlying data? What does that expose? But I also see here that there's connectivity from here to my, that's a HashiCorp vault. That's where all my secrets reside inside of my environment. So now, if everything's perfectly configured, the attacker maybe has access only to the secrets that are present already in this container. But I don't know that that's true. That's a thing that's potentially going to ratchet up the severity of this incident, give me a reason to go dig more fully in from here. Now, also from the flight data perspective, if I look at, say, here's an incident that happened on a Struts 2 container running inside of my environment. So we grabbed this. This was a port scanning incident. We can see that Nmap was launched. But if I grab my forensic data here, I get now a full end-to-end view of everything that happened in this incident, not just the alerts that Twistlock generated because there was anomalous behavior, but all of the steps along the way. So if I start at the beginning here, I can see this container started, and then something happened, and we see commands being run that are typical sort of recon, figuring out where the attacker is and what they have access to. So I can see they're running uname to see what they're running on top of. They're seeing what processes are running. They're running Nmap to map out the environment and see where they're sitting, which is why we got the port scanning. They're using Git to pull something called Mimi Penguin, which if I go dig is a password scraping tool. And they're doing some other things along the way here. They're copying, et cetera, password and exfiltrating it. So now I have a nice view, well, not a nice view, practically speaking, but a functional view of things that happen inside that container that I may not have been able to see from application logs, from host logs, etc. And now I can take this, I can download this, import it into whatever tool I'm pulling all of my investigation data into, and work with it from there. So let me, this seems like a good time to see if there are any questions and address, what's on everybody's mind.
Hi, Neil. Thanks so much for leading today's presentation. We've had a couple of questions come in and certainly have some more time if folks would like to ask those now. A couple of folks have asked, what does the threat landscape, against containers look like? And also, what are some of the most common incidents that you've seen for containerized environments?
So, and that's a great question. And what I find is, going through emerging technologies, what tends to happen is the early attacks are, script kiddies, I think is the common terminology, right? They're folks just joyriding, trying out things. So we saw that with lots of emerging, with cloud services when we were moving to sort of IaaS and SaaS there. And we're seeing that with containers now. Last year at DockerCon, the Twistlock R&D team presented about a thing that we found, which was that attackers were using containers to spin up Bitcoin mining, Monero mining. Monero mining is the most common one there because it requires less resources. It seems to be more profitable than Bitcoin mining now. But they're using improperly configured endpoints, improperly configured registries, and using those to drop those miners into people's containerized environments and run them. And from an attacker perspective, this is a fairly elegant attack compared to if you look at like ransomware, which was the sort of the big monetization approach prior to that. Ransomware is really ugly. You've got to write ransomware that's going to run on every machine you want to target, which may be every Windows machine. You may be focusing on some Macs as well, some other things. You've then got to not only make sure that runs, you've got to figure out how to distribute it to people, whether you're going to find a vulnerability or multiple vulnerabilities you're going to use. You're going to, use email spam, whatever else. And then at the end of that, you've got to figure out how to explain to end users how to get Bitcoin and send it to you. So in contrast to that, using an open Kubernetes endpoint or an unprotected registry to spin up your Monero miner is low impact. You can use existing tools to do it, and then you're just using somebody else's CPU to mint money for you. So I think that sort of thing has been the primary attack so far. And we saw this, we presented on this at DockerCon towards the end of the year. We added protections, runtime and compliance protections into the product in December. In spring this year, Tesla had a very public incident where this happened to a improperly exposed Kubernetes endpoint running in AWS. Since then, I've talked to at least half a dozen customers who've had similar incidents happen in their environment. And generally in sort of QA, pre-prod test environments. But certainly that's the emerging attack trend right now. But the thing is as the market becomes more mature, as the deployments become more mature, and as the things that are running become more interesting, we're going to see attackers transition from that into more targeted attacks, more focused attacks on data, attacks on financials, and that sort of thing.
I see some future content coming down the pipeline, as those types of things emerge and change. We have an architecture follow-up question here. How many nodes does a single instance of Twistlock support?
Yep.
And then what are the space requirements from a log storage perspective?
Yeah, so from a node perspective, a single console, the thing we were looking at, supports generally 1,000 nodes. There's always performance tuning going on there, but that's the round number. Now we can scale out across as many consoles as you want. Effectively, we can support an infinite number of hosts running containers. I don't think we've deployed on an infinite number yet, but hopefully we will soon. That would be great. But certainly thousands and thousands of hosts running containers is well within our wheelhouse. From a log storage perspective, it's fairly light. Of course, it depends on how much logging you're gathering. From a syslog perspective, we can turn on the floodgates. If I just turn on syslog, it's fairly light, but I can pipe out all the vulnerability assessments, all the compliance assessments line by line, which generates a lot more data. I can also turn on generating syslog out for every process that's started in every container, which is great data, but that's also a lot more data. So there's some tuning there. From the console perspective, our production sizing for console, for the data that console retains, 100 gigs, I think, is the production suggestion we have for that volume. In terms of the flight data recorder that's running continuously, like I said, that's a circular log. It's configurable. Out of the box, the setting is 100 megs. That's fairly lightweight data because it's really just metadata about things happening. Our testing 100 megs on a sort of standard medium-sized node was about 30 days worth of data for the containers running there. But obviously, once again, that's tunable for what makes sense for an organization.
Great. Thank you so much, Neil. I want to thank everyone who joined us for our live webinar today. Thank you so much for joining, asking questions. As always, we will send you a processed version of this recording that you can view again or share with members of your team. And as always, if you'd like to connect with Neil or the rest of the Twistlock team, please visit us on our website, Twitter, or contact us via email. Neil, thank you so much for leading today's presentation.
Hey, thank you everybody for joining.
Thank you so much, and everyone have a great day.